Hey, welcome to episode 24. So, this has been going on for a little while. We are about to get the last of the major code generation for our first pass, up and running. There's a few more major things we got to do. We're going to finish up the hash table stuff today, and hopefully finish up the emit stuff today. And then there's a few more details we need to emit, token kinds, and at that point we need to start seeing if this thing can build. We need to figure out how the emit function works is the other big thing we have to do. So we have a few more final things to figure out, but we're pretty close to having the Lexer fully up and running at this point, which is pretty good news. Once it's up and running the first time, we'll have so much gunpowder, backing us up. We'll have such strong firepower that going in and writing alternate versions, optimizing here and there, will kind of feel like free progress all the time. We'll have one that works, and then we can just improve and improve and improve it for however much time our heart's desire to see more improvement, right? That'll be the most fun part. But right now we're almost done. Let's focus, let's get this done. So around the end of the last episode, I realized that some of my notions about how we wanted to optimize the hash table were probably ill-formed. I had been mostly concerned with keeping the hash table small while avoiding collisions between the things that we insert into it. But that only makes sense if the assumption is that the common case is that the thing you're looking up in the table is in the table. But actually the common case, at least for this keyword table, is that the things you look up will not be in the table. In other words, if you take any identifier and you're saying, hey, I want to know if this is a keyword or not, the common case is that it won't be. Like if you look at my code at least, a vast majority of the alphanumeric sequences of characters that could be an identifier or a keyword if you didn't know the difference between them. The vast majority of them are not a keyword. The vast majority are actually identifiers. So I should be optimizing for making sure that the lookup of a thing that is not actually in the table is fast. And the way you do that is by making sure that you don't have to do long stretches of, okay, all these things are tightly packed in. So the way I had been doing it was keep the table small and find a layout that avoids collisions. Well, that's nice when what you're looking up is going to be in the table, because it means that most of the time you're going to have a nice small table, and the number of lookups will be however many iterations it took to do the insertion. So you just do some Robin Hooding and there you go. But that's not the situation we're actually in. The situation we're actually in is that the things that are not in the table are very, very commonly looked up, and we want to hit a null early in the iteration to tell us that that's not in the table. So what we actually want to do is go for a slightly larger, beefier table, let it expand out a little bit, give it a load factor closer to 0.5 or 0.6 than to 1.0, right? And at the same time, we want to measure our error not in terms of the number of iterations it took to insert something, but rather the number of iterations it would take to discover that to find a null if you hash to a particular slot. So if you hash to any of these slots, then you learn right away that you're not in the table. But if you hash to this slot, then you need to do 1, 2, 3 comparisons to learn you're not in the table. So we kind of want to aim for that, right? We want to aim for our error per lookup being around 1 to 2. So we still kind of right now, we're not quite leaning in the right direction. We're a little too big. Our error score is 132. We want our error per lookup to move a little bit closer to 1, in the 1 to 2 range. This is leaning towards 1. If it was 1.5, I'd be happy, because then that would mean we were getting a slightly smaller table, which we're not doing right now. So I want to kind of tune our optimization parameters again. I'm going to start by tuning the heavy optimization parameters, because those are the ones that we actually want to rely on for when we're doing a good job. Whoops, I switched to light effort. Do heavy effort optimization, please. We want this to be something that we can run that feels like it takes about a beat. This is taking a little more than a beat right now to find a result. And we want it to have an error per lookup. We want it to bias towards error per lookups that are a little bigger than this. So how do we do that? So for one thing, my acceptable error threshold right now is keywords count times 2. So the way this works is that the keywords is 66. So if I set my error threshold to 132, which is what it's at, then I'm saying that once we have 132, that's the number of errors I want, and 132 divided by 66 will give me an error per lookup of 2. But my table is going to be more than 66. In fact, my table starts off at three halves the original size, and then it grows a little bit more from that. So it starts off at 99, and it's going to grow more. So this error threshold is not actually quite high enough. Now the question is, how do I want to tune that error threshold? Because just making it like a multiple of keywords count feels a little bit wrong, because then the number I end up multiplying by is going to be fine-tuned for 66. But like if we come down here to the spot where the used count is 15, I think we'll find that the number I want to multiply by might be different. Now I'm getting an error per lookup of about 1 as well here, so maybe it's fine. But I think what we need to do is we need to find some way to relax these keyword count, like the error threshold, so that we'll allow a little bit more error, and try to push this error per lookup towards 1.5, right? And let the tables get a little bit smaller in the process. So first things first, if I did this times 3 divided by 2, what would I get? I would get 4522. So this is already actually at the smallest I'm allowing it to be at. So I'm going to say that this is growing our size too much. What we really should do is something more like start at maybe 5 out of 4 or something. So start smaller and iterate up from there. That's step 1. That might give us smaller tables just by itself. Still taking longer than a beat though, but just barely. So that gave me a slightly smaller table this time, but who knows? It's still not pushing the error per lookup at all. And by the way, another thing we haven't done yet is we haven't looked at our single error score. I would rather this be like a 1.5 or a 2 and have this get close to the same number. Right now, if I were to be calculating that, I would be getting like a 4 just because of this, right? So let's put that in there, because maybe we want to see how that's going as we're going. So up here's our error score. Equals 0. Max run length equals 0. And then what I'll do is every time I increment one of these, total run length goes up by 1. Whenever I see one of these, total run length, I guess total run length doesn't need to exist yet. Total run length can start down here, but this needs to do that the max run length equals the maximum of the max run length and the run length that we just got. And then down here, if we see a total run length of total run length should equal the run length, and then what should happen is that the total run length is still incrementing, and that's what's getting put in here. This thing that I'm right here is for wraparounds, so that's why it's set up that way, right? I'm starting with the run length that I left off with at the bottom, and then wrapping around to the top of the table, and as long as the run keeps going, I'm going to want to, first of all, I'm increasing my error score correctly to make up for the fact that I didn't know it was a wrap when I first put the error score in. But then the other thing I'm doing is I'm taking the total run length, and I'm incrementing it to find out my max run length correctly, and then finally, come up here to layout, we'll see I have this max single error score. I'm going to say instead of max run length, well, max run length is a nice small name that makes sense. I'll just say right here at the end, max single rank score equals max run length. Right? So there we go. Yeah. Okay, so now what do we get? Do we get a number there that looks right? This is the more important question. Alright, so we're getting a 4 here and less than 1 there. We want to drive those closer to each other. We want our max single error to be low, and we want this, although we want it to be low, this is lower than it needs to be. We could go for smaller tables with higher error per lookup, with this going down. Right. I'd like these to meet at about a 2 for this and 1.5 for this, or a 2 and a 2 or something, right? So I think what we need to do is just we need to just, hold on, opt key layout. We need to just stop doing some of these things the way we're doing them. So let's start with our init slot count is just back to the original key count, like the way things used to work. So we're going to start with 66 as the slot count for this. Well, we should start with at least 67 because the system won't even work. So I guess I still need the thing that does this. The idea of this is that for a table with just one spot in it, we can go ahead and just turn that, and we don't need to worry about the error at all. Then our acceptable error threshold, we want to change how we're reading that. We should call this the acceptable error per, like, relative error threshold or something like that. And that can just be a number that's like, we want about 1.5, maybe, why don't we say we want like 2.f, right? We want an acceptable error, relative error threshold, not an acceptable error threshold, because that lets us score against that F32 value. Now, that's a part of the debug print so far. That's not something we actually have in this section yet, but we can easily get it. So here we go. Here's our relative error. So when we're doing this, we get back an error score. What I want to see is, what is my relative error, which looks like that. And so now what we want to do is, okay, accumulated error threshold is probably wrong. That's also about the old error stuff. So why don't we say we're going to just go with an F32 for that as well, like accumulated error threshold equals, right? And I don't know what the bottom part needs to be yet, but the top part, we're going to say the accumulated error threshold, we want to let you run, it says here we're going to let you run about 6,000 times, and we're going for 2.f, so I'll give you, let's say I gave you that, what would that mean? That would mean that if you were achieving an error threshold of 2 every time, that you'd get the full 6,000, and that if you weren't achieving that, you'd get a little less. So that's good. So like if your error threshold, if your relative error value is like a 4, which is twice as big as what we want, then you have half as much time on that layer before we say this table's too small, increment the table by 1, right? So that makes some sense. And if it's like way bigger, if it's like we're getting relative errors of in the hundreds, then it's only going to give you a few chances. You get like maybe 100 chances, right, to find your results, maybe less, maybe like 50 chances. And if it just isn't working out and these things are huge, then you're going to get skipped very quickly. We'll go to a smaller, slightly larger table. Now, the question that raises is, what's the point of layer max number of tries anymore? Does that actually achieve anything these days? Or is this accumulated error threshold all we need? So the only thing this was, I think, ever achieving was that there were situations at some point where the accumulated error threshold lets you go on for a long time, and we just wanted to say, look, I guess it was for cases where if you ended up getting, like, your acceptable relative error was at 0, but you're never going to get that shit right now. Like, you're just always going to have some error, because the way we're measuring error, it's impossible not to essentially get some error. So I think that can go away. And so what do we have to rewrite to fix up for this? So relative error, key layout. You just call layout. You call that layout in this part of the code. That's not a part of this anymore. You're just always going to put the relative error in there exactly as is. So accumulated error is a float now. Try counter can go away. We're not doing try. Oh, we're doing total try counter, I guess, right? Our total try count. Wait, no, our try counter's gone. We're not doing total try count. We're not doing layer try count. Okay. Best layer error score is less than the acceptable. Okay, so what we need to do is we need to we need to actually store this relative error. So this is our error score here, and max single error. We actually just want to store like our relative error right here, so that we can do this a little differently. So when we get our max single error score right here, we're also just going to go ahead and compute our relative error right there. Okay. And so now, when we get a layout, and we're trying to optimize it, what we're going to do is we're going to say we don't even need to compute the relative error. That gets done automatically inside that function. So, you know, we'll just use the copy that it made. Relative error. When we go to debug print, by the way, a table at this point, we shouldn't be computing that either. We should use the relative error that the key layout is reporting directly. Relative error. Okay, so back up here to relative error. So if the relative error is less than the acceptable error threshold, we're not calling it relative error all over the place anymore. It's only going to be there. So if it's less than the acceptable error threshold, and this is the first time we found a first acceptable error score, then we're going to take our accumulated error threshold. Yeah, that's still a thing. And we're going to say, give us this much extra effort. So we give ourselves a lot more extra effort once we're on the table count that we found a solution for. So the basic idea is we need to achieve this threshold, and then we've solved the layout problem. We know that we have a solution, but we can still optimize it. So we've hit the acceptable solution, so we're going to stay on this layer forever and never grow the table and see if we can beat that solution for a little while. And we don't have that part anymore. So the max, this is just can be an F32 now. That's like, look, you get 400 times more effort on the last layer, since you're not going to be spending any time growing the number, like growing upwards to find more larger slot counts that achieve the result we're looking for. Let's just imagine you were going to do 400 more layers and put all of that effort into this layer instead, right? Layer try counter is greater than or equal to layer max number of tries. That is irrelevant, so it only matters if we hit the accumulated error threshold. Again, remember, accumulated error is always going up because the relative error can't be 0. The relative error is always at least non-zero. It could be very small for large tables, but we're not really going to let it get to a gigantic table without kind of capping things off there. We may want a thing that caps off the number of tries you get on the last layer, because if you're getting like values of, 400 might just be too much. Like, it might be that since we're doing this, what we're basically saying is you're getting about 6,000 tries per layer. If at that layer you're getting pretty close to 2 but not hitting it. As soon as you get below 2, you get more than 6,000 tries. You get 12. Like if you're achieving a 1, you would get 12,000 tries. But as soon as you're below 2, you're close enough, and so you're going to be getting about 6,000 tries. Times 400 means you get about 400 times more than that, which is what, 24,000 tries, 240,000 tries, something like that. 6,000 times 400, 600,000. So it'd be 2.4 million tries. That's what it would be. If that's too many, we can just tone back down this extra effort on last layer. So what I usually would like to do is just figure out where it roughly lands, and then the extra effort just helps us get better scores. It doesn't help us get smaller tables. So I'll leave that there and see what kind of table this achieves without it first. And that'll run nice and fast now, and then we'll be able to figure out how much extra effort to put into optimizing the table on the last layer. Okay. So, the relative error is less than the acceptable threshold, blah, 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 accumulated error is greater than that. Then if the best, we want to check if the best layout. So what I actually want here is if the layout's relative error is less than this guy's relative error, then we do this and we check out if the layout's relative error is less than that, is less than the acceptable error threshold, then we're finished. Okay. And layer try counter, you're nobody, you're nothing. Okay, let's see this in action. Yeah, so that finished right away, started with a slot count of 0, and it had an error. So what the frick? What the frick? First of all, let me make sure this isn't like looping or something. No, looks like it finished without crashing. But why did it go for such a slow slot count? Slot count equals keywords.count plus 1. It should have been 67. And it comes in here. Yeah, I don't understand what's going on. That's weird. I think I need to step through that because that doesn't compute at all. So, show me what happens when you try to optimize this table. You have a slot count of 67. We set up some parameters, and I see. You eventually are going to hit this, and the best layout never gets set to anything because, right. So it's no longer max U64 that I care about, it's that the relative error starts off as max F32. Okay, so now you're finding a slot count of 93, which is good. That's less than 2/3 even, so we're getting a pretty decent load factor. Your max single error score is all the way up at 8, which I do not appreciate. I was kind of hoping that we would find a way to drive that number down at the same time as letting the error per lookup go up. And the problem is, as we try to drive it down, we're going to have to let the table get bigger. So, I think the move is going to be, let's say we want that to be a 2, right? I don't even know. These parameters here will be determined by how the heavy optimization turns out, and they'll just be tweaked to go a little bit lighter weight and a little bit more random-y. But if we allow for an error threshold of 4, and I take relative error, and I say relative error is based on... Okay, so relative error isn't quite the right thing. I want sort of a... I want the relative error is more like the iterations per lookup, and then relative error is going to be something based on that. Relative error, iterations per lookup. And now, if we take iterations per lookup, and we multiply by the max single error score, then we get our relative error. Right? So now, it needs to drive this down to a 4. So the product of those two things needs to get closer to 4. So either it'll be allowed to go for a 1 here and a 4 there, or a 2 here and a 2 there. I'm curious to see which one it reaches first, but right now I'm going to just let it do it that way. If that doesn't give me closer to what I want, then what we'll do is we'll say you need to move towards weighting this more strongly somehow than this, right? Maybe what we do is, yeah, well, we'll see what we do. I have some ideas of how to weight it more strongly, but so you can see here, okay, error per lookup is not right. This needs to be iterations per lookup. So there it went for the 1 and 4, and you can see it went for a table size just a little bit under double the thing, which is good. That's kind of what I was expecting. So now I'm going to try to change the weighting. So right now I'm multiplying those, and the problem is that lets it drive one of them towards 1, and there's only one that can get to 1 first, and that's the one that is getting to 1 first, so I'm going to change it. And the way I'm going to change it is say that the relative error is going to be the sum of these two things, right? So now if it leaves that at 4, it's still getting a score of 4. It's got to get that below 4, and the sum of these below 4. So it could go for 1 and 3. We'll see how it does. That's kind of what it did. So it went for 1 and 3, which I'm pretty happy with. That means that if you ever do a lookup, on average, you half the time, like your average cost of a lookup is 0.6, right? And the worst case lookup cost is 3, and by lookup cost I mean the number of comparisons you have to do to find it. Problem is this is leading to our table being too big. So I wish I could find a way to get it to spend more time looking for something with the max single error score that is low once it hits the point that its error per lookup is below 2, right? So it's kind of like I want it to get the errors per lookup, like the logic is first iterate towards finding a spot where the error per lookup can be below 2. Now you're still allowed to grow the table, but once you've found that spot, you know that there you can get the error lookup below 2. You're no longer scoring yourself on that. You're now scoring yourself on, you have to keep the error per lookup from growing ever. It must not grow. But you are choosing options, like you are switching to things that have smaller max single error scores and keeping them around. So right now I don't actually do that directly, and I might want to. So I guess let me write out sort of like pseudocode that describes the logic I want to do. It's like step 1, find table size with error per lookup less than 2. Then what I want to do is find table size with max single error, and this will be like low effort mode. Then I want it to switch into high effort mode with single error less than 2 without letting error per lookup increase. So essentially, for something to replace the existing solution, it has to have a better max single error, and it cannot have a worse error per lookup. So this will actually have to be smaller too, but this being smaller won't be a criteria, like won't be a good enough criteria. It'll simply be an elimination criteria. Anything that where that goes back up, you can't use it. But if it doesn't go up, or if it stays the same or goes down, you can use it. However, you can only even get to the point where you're going to use it if it has strictly decreased this number, right? And so hopefully that would lead to it keeping smaller and smaller versions of this until it got down to 2. And we do this with high effort, meaning we search a lot of possibilities at a particular table size before we move on. And then as soon as we find it, we would say good enough and be finished. Right. Right now the high effort kind of just sits there trying to lower this total score, this total relative score thing, but that doesn't seem to be getting me what I want. So I'm going to try this alternate approach. Let's try it. When this reports what it reports, it gives me max single error score, it gives me iterations per lookup, so I can do this. What we're going to do is say that the logic goes like this. I'm going to ignore what I've kind of got there and just write a new one from scratch. Relative error. Okay, so I'll start with this concept still. We're going to be increasing our slot count, and the only difference is I'm kind of going to do this as 2 separate loops. So init slot count is going to go there. We're going to be increasing our slot count at each step. What we're doing at each step, we'll do the accumulated error thing the same way. So this is all, okay, maybe I could have kept the same code. I'm not sure that that's still relevant. Accumulated error, we grab a seed, we lay the thing out. We're going to do the accumulated error to determine if we need to move on. If we hit this, then we're going to say, okay, we've hit the, yeah, let's get rid of relative error as a separate concept. Relative error. This is going to be iterations per lookup. So we're starting by trying to get our average iterations per lookup below 2. Iterations per lookup. Iterations. Less than your iterations per lookup, then that's our best layout. And if our iterations per lookup is less than the acceptable error threshold, then we want to say, okay, we're done with loop number 1. So accumulated error, this is just going to be iterations per lookup, and go to optimize max single error. So once we are done with that stage, we go on to the stage optimize max single error. And this part, so we still want to pull slot count out like I was going to do before. This part continues right where that left off, same slot count, same best layout that it's found so far, except now what we're going to do is switch into like high effort mode, right? This is kind of what we used to do, was when we hit this we gave ourselves a much bigger budget to stay on that layer forever. Now we're switching to high effort mode, but high effort mode can still increase the slot count one by one. And in high effort mode, so we don't need extra effort on last layer. What we actually need is like acceptable lookup per slot, right? Or acceptable max single error is, I'm going to set it to 2 for now, see if we can achieve that. And then we'll have accumulated max single error threshold. And the answer is, okay, let's do, this is high effort mode, so instead of 12,000 like this, we'll do 120,000. How about that, maybe as a starting point, right? Give ourselves 10 times as much work. Let's actually go higher than that. Let's go for 600,000. 50 times more effort per layer, looking for ones that do this, right? Maybe that'll do the trick. So we keep on grabbing layouts. This time we're starting with a concept of accumulated error being 0 that is a U64. The accumulated error comes from max single error score. If the max single error score is less than the max single error score we already had, and the layout's iterations per lookup is less than the accumulated error threshold, right? So we don't want to go back above the threshold. I guess we'll allow this to like vary around just as long as it doesn't go back above the threshold. Then that's our new best layout. And if the max single error score gets below the acceptable max single error threshold, or gets below the acceptable max single error, then we're finished. If the accumulated error ever gets above the accumulated max single error threshold, then we break out of this loop and go to the next slot count. See if it can do it. That might be too much effort. I might need to be able to put in less effort per slot count to find this, because it might be that it just needs to get to higher slot counts before it'll find results. And so having less effort per layer will let it get there faster. Could also be that this is just unachievable and that I should settle for a 3 instead of a 2 as my max single error. But let's give this 2 minutes to run, see if it finds anything. And I'm going to go turn the lights on in this room while we wait. Again, I haven't written in a progress indicator, which is bad form. All right. Because I don't have any way of knowing if, for instance, this is getting caught in an infinite loop in a different table or something. So I might not actually give it the full 2 minutes. I'm going to say let's cut it off here. There we go. Let's cut it off here, and let's run it again before we spend too much time sitting around. Let's run it again with a couple of tweaks. One, I'm going to say, well, you know, before we do anything else, let's just put in the progress indicator, because I don't want to, you know, I don't want to start throwing out something that might have been perfectly well designed, for all I know, just because there's like a bug that's leading to an infinite loop in one of the corner cases or something. So before I get myself all confused and start telling myself that this is unachievable or that these numbers don't have the result I want, let's put in the progress indicator and see what's actually happening. Okay? So what we want to see is at each step, let's start by saying we're going to print out the slot count that we're trying every time we increment that. And we're going to say that we're going to, every time we lay one of these out and get a better result, probably, that's where we're going to say new best error %f iterations per lookup, and then here new best max single error max single error, and that should actually be that. Okay, I don't see any of those showing up, which suggests we're actually in a loop that's going on infinitely, because some of those, like, it's the reason that suggests we're stuck in a loop that's going on infinitely is because it could be that it's trying to buffer, like that it's doing buffering, and so none of this stuff is coming out yet. So I really need to do, if I really want to see these coming out immediately, oops, not dev, I want to turn off the generator. I could add in flushes, but that doesn't always work the way I want it to. The more surefire way to see results immediately is to just make sure that there's always a little bit of stuff coming out all the time so that the buffers fill quickly. So every time I do a layout, I guess what I'll do is this. I'll add in one of these as well. I guess we already know when that's happening. So new layout, %LU, max single error score. Let's see if I can see anything coming out now. There we go. New best error 33, new layout 33 over and over again. Weird. Okay, that's bizarre, isn't it? Now the new layout stuff actually leads to different results. New best error 16. Okay, that makes sense, but why are these all 33s? What is going on here? How would it be possible to get a 33 every single time? So the relative error, or rather the iterations per lookup, things are going to run really slow because 4coder is getting slammed with lots of inputs. But I'm going to let that keep running for a minute while I look up how could this get the same result every time it goes through. Its error score and slot count aren't changing. Ah, right. Because I start with a +1 as the slot count, that makes perfect sense. That it's getting the same thing over and over again. Alright, let's just say great slot count. Every time the slot count goes up, it means that progress is happening. And if we go up far enough, hopefully we'll see where it switches over to best layout. I want to see the new best layouts. Okay, well, in this section here, it is now trying to optimize for max single error. Wait a minute, did it go down to just 4? Did I not change the 4 back to a 2? That should have been a 2 for one thing. Yeah, okay. Okay. So this was in a situation where I was putting in high effort and it wasn't even close to the right size for it to find what I was looking for. So it was spending a very long time on each slot count. You can see it's like 87, it is like 100, 20,000 tries there, 20,000 tries here, all for the sake of almost a little over 20,000 tries, all for the sake of finding a small number that is just not going to happen at, like, see, right, like, it's putting in that much effort to find a really small number when these numbers are all that big. So kind of what I think is happening here is that my accumulated error score needs to be like squared or something, right? Or like we need to take the number we have, divide by the number we're aiming for, and then square it, and then multiply the number back in, or something like this. We gotta normalize it somehow, because the number we're aiming for, right, should be what it expects to be. So like, basically, if we're getting a 2 out, we should have a 2 as our thing we add in. But these should have been like, if we're getting 30s, 14s, and 23s, and 24s a lot, it should just know that it can't spend that much time there. So I kind of think what I should do is make 2 adjustments. One, it's going to help that our new best error has to get down to 2 first, because these spend a lot less effort per slot count, right? So it won't bail as soon as it gets to 4, it'll have to get to 2, so it'll spend a little more time in the low effort mode. Once it switches to the high effort mode, though, I think we want it to adjust a little bit. But let's see what happens first when I just switch that to 2. Okay. So it's spending time shrinking. New best error. I want to keep track of how good it's doing. 2.4, 2.3, it's finding its way to 2.0, 2.1, 2.1 again, 1.8. So there we go. At that point, it discovered that at 91 or at 92 slots, it can get to an error of 2. Now, it's still looking at these numbers and going, wow, these are huge. These are huge, so it's correctly thinking we have to keep going, but yeah, these are so big that it should realize that it's just not even getting in the ballpark that it needs to get into, right? Like, it's trying to find a 2, and the lowest thing it's found is a 9. It should know to move on sooner than it does. If it was getting like lots of 3s, I would want it to spend this much time. But it's getting lots of 20s, so I'm going to try something. I'm going to say, let's keep this exactly the way it is, and let's just come in here and say, when you get your max single error score there, we're going to say adjusted error score is achieved by taking max single error score, dividing it out by the acceptable max single error, and then squaring it, and then multiplying back in that max single error. So if you get to a number smaller than the max single error, then this will turn into a 0, and that's fine because you're about to exit anyway. If you get exactly what you're looking for, this will turn back into itself, which is fine because again you're going to exit right away. Anything bigger than that, if you're one bigger than it, you're going to turn into something roughly close to where you started, because when we divide by this, you're going to become a 1 squared. So I guess that'll be a problem, right? So if I have a 2 here and I get a 3 here, this will turn into a 1. This will square back to a 1, and then this will multiply to a 2. So it would actually go down. So to encourage this to never go down, and by encourage I mean guarantee that it never goes down, what we'll do is we'll add in an acceptable error -1 here. So we're doing a division with rounding up, right? So this rounds up. So a 3 divided by that becomes a 4, right? Divided by that becomes a 2. Square it becomes a 4. And then multiply the 2 back in, it becomes an 8. So a 3 by itself is already scoring an 8. You put in a 4, you get the same thing. You get an 8 out. You put in a 5, you would get 3, 9, 18. Right? You put in a 5, this becomes a 6. Divided by 2 is 3. 3 times 3 is 9. Back times 2 again is 18. So yeah, anything big will blow up much faster now. You'll have to get down to the single digits in order to even last as long as this is lasting. Right? So this is currently doing like 12, 32, 25, and it's spending a very long time there. It'll still spend that much time when it's in the like 4, 5, and 6 range. Even in the 7 and 8 range, it'll spend a lot of time the way it's spending time here. But when it's getting 10s, what will happen is it'll turn into 25, it'll multiply by 20 and get 50 as its adjusted score. And so then this is going to be going up like hugely fast, right? And it should not spend as much time in there. So new best error, 32, 27, 18, 17, 16, 16 again, 16 again, 16 again, again, 15, 13, 11, 11, 11, 9, 9, 9, 8, 8, 7, 7, 5, 5, 5, 4, 4, 4, 4, 3, 3, 3, 3, 2, 2, 2, 2, 2, 2, 2. It's trying hard. It's trying to find a 1, 2. Haha, 1. So at that point, it's now below the threshold, and now it says, alright, we found a spot where it's conceivable that we get below the threshold, so let's start putting in the effort here. So the problem is, we've only discovered that it's conceivable we get through below the threshold, but a lot of the time we still won't. So a lot of these are going to get ignored just for not even being below the threshold. But at the very least, we shouldn't spend as much time on a single layer anymore, right? So let's see, 38,000, 41,000. So that only took 2,000 lines instead of 20,000 lines, right? Now what I want to see is, is it giving me a new best max single error ever? So there it got it down to 5. Four, Hasn't found it yet. Hasn't found it yet. Hasn't found it yet. So you can see here we're getting a large mix of 20s, 10s, and high single digits. So hopefully it's not spending too much time per layer. I'd kind of like to switch back to seeing how the slot count number is doing. So it's now trying 129, which is still not even double the size of the table yet. $130. So it's still taking its time incrementing that table size, hoping that it'll find a result without having to increment. And that's kind of the idea, is the more effort it's putting in, what that really just means is it's spending more time trying things, hoping it'll find one. And the problem is we don't even know how many of these are even close to useful, because we don't know how many of them are still not hitting the thresholds for occurring, but we know for a fact that none of them are giving us a new best, or at least not another new best of 2, because they would have stopped. It might have gotten to a new best of 3 by now. Let's take a look. New best max single error. Whoops. Can't have it misspelled or it won't find anything. Single error. If I go up. Last time you found a new best max single error, it was a 4. So the other problem we have here is that it's running way slower than it would if it wasn't trying to print all the time. So now that we know that it's kind of coming out correctly, what I'm going to do is I'm going to change a couple details. I want to stop doing all this printing now. Let it run a little faster. So we'll take out the thing that just does that part, and hopefully the rest of the information it's printing out is still enough to give us feedback eventually. It might not be. We might not get enough feedback opportunities now. Okay. Let's try this another way. Let's see if adding in the flushes actually helps. Sometimes it doesn't, but sometimes it does. There we go. Now it's running way faster. You can see how big it's trying to get to find that 2. That 2 might be just too much for it to try to find. It might be beyond reasonable. Hey, it found it. Now why hasn't it stopped? I couldn't tell you the answer to that question. It's probably looking for something less than 2. So is less than or equal to. Yeah, these should be less than or equal to acceptable error threshold. It's less than acceptable error threshold. It's less than or equal to max acceptable single error. There we go. Let's try that again. Okay, so we can see it going. It's found the 5, it's found the 4, it's found the 3. I think 2 might be too much to ask, because this is way bigger than, this is going to be like triple the size, maybe even more, before it finds it. Right. So yeah, this is more than triple the size. It has an error per lookup that's super low, and it does achieve a 2 there, but in exchange for that, we're filling in so much space with nulls everywhere. So by achieving a 2, what we've just achieved is we've got no more than 2 in a row here. I think that's just, that number is too low. I think 4 would be enough, you know? 4 should be good enough for what we want. And what that means we could do is we could say, let's look for a 4. But while you're looking for the 4 down here, I want you to actually be a little bit more strict. You need to keep on improving your iterations per lookup perpetually too. And oops, I thought I killed it. End that process. And so that might make it take a little bit more time to find it. There we go. So there we go. Now that's pretty good. We haven't sacrificed our load factor too much more than we already were. We're between 0.5 and 0.6, which is where we were. We're a little bit smaller on our table size than when we started all of this, which it was getting around the 120s before. This might be a fluke. We still have to take a look at that. And we've guaranteed that our table has no more than 4 in a row anywhere. And that we've also guaranteed that the average is less than 2, right? The average error per lookup is less than 2. So what else could be done? I don't know what else we could do there. Is the generator still running? So I think it's getting caught in an infinite loop after that because I think something later isn't happy with how this algorithm is structured, so we need to take a look at that. But that's fine. Let's do that. That's fine. Okay. And here it is, the one that probably needs to get looked at. So what I want to do is I want to say, look, I know where things are going wrong here. What am I doing looking at this file? This is not relevant. Thank you. I want to see, yeah, when you come in here and you do ask for optimization, tell me when this situation arises. Here we go. So, acceptable error threshold 2, accumulated error threshold 12,000, acceptable max single error 4, accumulated max 600,000. Slot count 1, accumulated error 0, C random, restore point, layout. What do we get? So its slot count is 2, which I don't like. Iterations per lookup is 0.5, so it should immediately recognize that situation. Come over here. It's going to do another layout, which is unnecessary, but it's the way the system works. And here it gets another slot count of 2, and its iterations per lookup is 0.5. Its max single is 1. 0.5, 0.5. Iterations is a max single. Ah. So it already had a max single error score of 1. So this logic assumes for a fact that the max single error score here isn't good enough. But what we really need to do is say, hey, let's actually take a look when this situation arises before we begin this loop, if the thing we found is already, you know, good enough that we should go to finished. Because if it is, then we should do that. Alright, that's step number 1. So when we get here, if we've done a table layout already that achieves the goal, if our best layout, max single error score is less than the acceptable, it already reaches that threshold, then go straight to finished, right? You don't need to do this loop. So that should just do away with the infinite looping. And there we go. Now it hits exit pretty quickly. Um, we can get rid of all this extra printing stuff now, because that was all there just to help me figure out what was going on when it was infinite looping, / when it was taking forever to find a result. And now that's not happening. There we go. So it took about a beat, which was good. Error score 134, 1, 4. Yeah, okay. Okay. That's kind of where we were ending up earlier, except I think we managed to make the table smaller by putting in more effort when we were trying to get this down, and less effort for this. We could probably fine-tune it a little more, because I think we could afford to put in even more effort during the second stage, and less effort here. So just to play with that idea, not going to spend very much time on this part, but let's try dropping that down so it has less effort put in there, and bopping that up so it has a little more effort put in there. Yeah, it's going to do just about as good. But I think that slight tweak makes the whole thing run a little faster, because it just tends to get us into an even easier... By putting in less effort here, we're making the tables turn out just a tiny bit bigger. And we're also finding them faster, like we're finding that point in the table faster, that table size faster. And so then we can trade that away and get a little bit more time to optimize there, and so that the incrementations that happen in that section, less increments have to happen before we find the 4. That's my theory anyway. And you can see that it's being pretty stable. It's hitting that 115 every single time, actually. So having that really high effort there is paying off in the sense of it doing a good job of finding the 4. The other thing that can bite us is if this low effort section doesn't luck out. But I also need to fine-tune this to have a version that is not high effort. So, whoops, that's not what I wanted. So let's try this. So how do I tune this for less effort? Well, the things I want in a low effort one is, first, it needs to take a lot less time. So let's say we just cut everything down by a factor of 10 in terms of amount of effort, and see what results we are getting from that. Okay, so that's much closer to instant. The size has gone up by about 10 slots in exchange for that speed, but we haven't given up any of our like quality of the solution in these factors. I'm going to also just say let's give up one more of these, because that's going to make it way faster. Yeah, that's pretty good. So with that, it actually ends up at a smaller table, which makes sense because it's a much easier thing to find, and I can probably cut back on the effort here even more. Yeah, and it's still going to find a pretty fast, pretty small, like it's not going to do that much work. The disadvantage to this, of course, is that now we have a max error of 5, but I feel like what we could do, we might just give it a little bit more effort at the head end, so that it'll have to deal with slightly smaller tables, and maybe it'll do a better job of going. Maybe I could, yeah. I'm noticing that it doesn't have enough time to get this threshold, this number back down to a 1, which is what it was doing before, so the whole thing is a little bit worse. And I'm hoping that if I tweak it just right, it'll try to get that a little lower. This is essentially the same pattern that it used in the other one, which is that in the old way I tuned it was that it had to have a stricter error threshold here, and a looser one here, or maybe it was the other way around, I can't remember. I think it was stricter here though, and the reason for that was so that it would spend a little more time finding large table size. Here, I'm getting it to find a small table size already, so maybe I don't know. Maybe it needs more effort here. There we go. Then if I drop this down to like 1.2 and say, please don't go over that. Okay, it's a little less than instant. Still a little less than instant. Okay, now that error score has gone up pretty high again. Remember, this one looked like this. Pretty regularly hitting that 1.1 area, and I'd like for this to try to do that, but it might just need to have more effort here than it's getting to do that or something. Well, that effort actually is just about how the amount of effort it puts in is about keeping the table small. So if I just drop the effort way, way down, but say you have to find like a 1.1 solution, then it'll find one with a large table. Whoops, but only if I run the light optimization mode. Right, so now it's just letting that table go up a little bit in order to hit that, which I think is probably better. Let's give this a tiny bit more effort. And there we go, that's pretty good. Cut your effort down just a bit more. Yeah, it's going to have to be that. So there we go. That's our light optimization effort mode. And so the main difference between the two is that this manages to find the 4 instead of the 5 at a similar table size. Cool. Alright, so there we go. Better optimization plan. We don't have time to write the rest of the emit handler, so that'll be the next episode. We're going back to writing the emit handler for keywords now. Alright, see y'all next time. Bye-bye.